All right, everybody, let's get started. Good afternoon, everyone. Welcome to the North Carolina Museum of Natural Sciences. Welcome into the SCCU Daily Planet Theater. My name is Chris Smith. I am your host for the Lunchtime Discovery Series. This is the opportunity we take every Wednesday at noon in order to meet interesting people doing interesting work out there in the worlds of science, technology, engineering, mathematics, art, education, conservation, and beyond. And we always have a great time because we meet fascinating people. They tell great stories. They share interesting science with us. We get a really great sense of what's happening in the world around us. Very excited for today's presentation. Maybe you have seen the movie Twister. It's a little bit of an old movie at this point, but has anybody seen the movie, the new one, the sequel, Twisters? Anybody? There's people in the theater who are nodding, their hands raised. People watching online, if you've seen either of those two movies, let me know in the chat. You can jump into the chat on YouTube, leave your comments, like, your Rotten Tomatoes score for it, thumbs up, thumbs down. Maybe you liked the movies, maybe you didn't. But the folks over at the Office of Environmental Education within the Department of Environmental Quality reached out and found an expert on tornadoes and severe storms so that whether or not you like the movie, we can figure out if what you saw in the movies was good science or not, which is every nerd's favorite thing to do, is to know, is that thing that they did in this movie real? Could you actually drill a truck into the ground and then have a tornado pass right over the top of it? I don't know, but the person who might know and that we've decided to give a call and check in with is a research meteorologist with the National Oceanic and Atmospheric Administration's National Severe Storms Laboratory. Everybody, put your hands together and welcome to the Lunchtime Discovery Series stage, Dr. Sean Waugh. Hi, Sean. How are you today?
Doing great. Thanks, guys.
I hope that now you're not in Raleigh, North Carolina, are you?
No, that's correct. I'm actually in Norman, Oklahoma at the National Weather Center.
Oh, wow. Oklahoma must be a good place to go study severe storms and tornadoes.
It is. It definitely is.
Well, I'm interested for your presentation. Of course, I'm excited to dive into the science behind the films, but to also learn a thing or two about tornadoes, which we are no stranger to in this part of North Carolina as well. So I will turn the stage over to you and excited for your talk.
Awesome. Thank you, guys. All right. So we're going to get started here. If there are any issues, if anybody can't see the screen, just go ahead and, cut me off, let me know, that sort of thing. But thanks for having me, guys. I'm really excited to talk about this. We're going to talk about the real science behind Hollywood's blockbuster movie Twisters, which came out, that hopefully everybody went to the theater and saw at least 20 different times. I know I've seen it at least 5 at this point, but it's a really fun movie. Before we get into that, just a little bit about who I am. I am a research scientist at NOAA's National Severe Storms Laboratory, which, if you didn't know, is located at the National Weather Center here in Norman, Oklahoma. It's a beautiful building. It's a great place for all things weather-related research. We've got the different Weather Service offices here, the Storm Prediction Center, a lot of private and public institutions as well. I have 3 degrees in meteorology from OU, and a lot of what I actually do is engineering, so that really prepared me well for my job today. But essentially what we do here at the National Severe Storms Lab, and what my job is designing and building a lot of the research equipment that we use out in the real world to study things. And that picture in the lower right there is a very old picture of me as a graduate student, or maybe even an undergraduate student at the time, kind of working on some of our equipment and vehicles and that sort of thing. But I've been doing this for about 20 years. I've seen a lot of different types of weather phenomenon over the country, even the world. We study tornadoes and lightning and hail, flash floods, even hurricanes. I've actually been out into the North Carolina area. We went to Hurricane Florence a few years ago. So we've done a lot of different types of work in a lot of different areas, and it's a really unique challenge to try to study that, right? Expert in observations, instrumentation, sort of designing that equipment that we need in order to study the world around us. And then recently I was able to add, consulting on a film to my resume, which was not on my 10-year plan when I graduated college. But hey, you never know where life's going to take you, right? So just a little bit about Twisters. That's where we're going to kind of start off this talk, talking about the movie and, what we see in the movie and where that sort of inspiration came from. And if you didn't know, the budget of the movie was about $255 million. It made about 365 the last time I checked. So, they're hoping, I'm hoping that maybe we see a sequel at some point. I don't know if we just keep adding S's to the end of the movie for that. But I was really excited to see it do so well that so many people seem to have loved it. A few fun facts: it was filmed entirely in Oklahoma, and that's part of the intentional effort that the filmmakers made to make it as authentic and as real and genuine as possible. So they definitely filmed everything here on location. And then there's actually a Warren, we call it the Moore Warren. It's an IMAX theater here in the Oklahoma City area. It was actually hit by an EF5 tornado in 2013. It survived. It was very well-built structure. It was a good shelter space for everybody. That was actually the highest grossing IMAX theater on opening weekend in the entire country. So there's a lot of meteorologists here that were really excited about it, that went to go see it multiple times. The cast and crew was absolutely amazing. I mean, Glenn, Daisy, Brandon, Anthony, Sasha, Katie, all of them. They're phenomenal people, and it was a lot of fun to work with them throughout this film. If you have not seen the film, I'm going to go ahead and warn you now. There are probably going to be some mild spoilers here. So if you haven't seen it, listen with caution, right? It's been out for a while, so hopefully everybody's had a chance to take a look at it. So the biggest thing that I wanted to point out to start with is that Twisters wanted to get the science right. If we watch the original movie, I love the original movie, and it is horribly inaccurate. It has so many things that don't actually reflect meteorology and what we do today. There's a lot of jargon that's used incorrectly, and the equipment is not real equipment. It's not something that we do. That was very dramatized. And when they started to make this movie, a good friend of mine and my former boss, actually, his name is Kevin Kelleher. He was the former deputy director here at the lab. He consulted a little bit on the original movie, but he got brought in really, really early in this movie to sort of advise on the script elements and make sure that the movie had those ties back to realism. And he actually showed up one day with Lee Isaac Chung, the director of the movie. And I had no idea who Isaac was. I just knew that Kevin was a pretty important person. And if he's giving a private tour to somebody, especially when he's retired and I haven't seen him in 5 years, that this person must be pretty important. And I later realized that it was the director of the new movie. But Isaac just absolutely fell in love with a lot of the equipment that we have here that we use to do severe weather research, right? We've got these big mobile mesonet vehicles that are essentially mobile surface observing stations. Things like temperature, pressure, wind speed, wind direction. We can do all of that while moving. And they've got hail cages and all this equipment on it. It looks like Home Depot just exploded on top of the car, right? We have these old ambulance type vehicles that we've used. We don't use them as much anymore, and we actually got rid of them recently. But they were mobile command centers that we had that had all these racks of computer equipment and monitors and things that we would use to monitor the weather and the data when we were out in the field. We've got mobile radars that we use, because a lot of the surface radars that we use that you look at on your phone, for example, they're really, really good for covering large areas. But if you're trying to sample things like tornadoes close to the ground, you need to get a little closer and a little lower, right? And then we started talking about the really exciting stuff, like the new technology, like the phased array radar system that we have here in Norman. It's called the Advanced Technology Demonstrator. And essentially how it works is it steers that radar beam electronically by using hundreds and thousands of different little electronic elements rather than a dish. So that allows the beam to move very quickly, and we can scan large areas much faster. And it's that new wave of technology that we're sort of trying to implement now. And Isaac just fell in love with all of this imagery and really wanted to make it a part of the movie to give that movie that like authentic, genuine feeling, right? So I mentioned earlier that Kevin was involved really, really early on. He had a huge role in writing the script along with the writer, Mark Smith. They created a lot of story elements and kind of went back and forth on things and really wanted to bring this story to life with something that was physically plausible. It maybe is a little exaggerated. The scale may be off, but it's based on sound theory and a lot of the equipment that we use today. So the goal is to make it authentic, right? And the best way that you're going to make it authentic is to actually make the equipment look the way that it's supposed to. And the prop teams and the set deck teams, they actually came to the Weather Center, and I spent a lot of time talking with them about the equipment that we use. And one of the things that we started off with was the equipment rack that we have on our mobile mesonet vehicles. They absolutely loved the way that it looked, but they wanted it smaller, and they wanted it to be made to mount on some of the vehicles that they were going to use for the movie. And I, in talking with these absolute legends in the film industry, I mean, these guys make all kinds of props. And here I am, just, a lowly research meteorologist. And I told the props team, I was like, hey, I do this for a living. Let me help you. Let me do this for you, for free. I'll build this in my garage, but I do these all the time. Let me make them for you. And they were like, great. That's one less thing we have to make. So I gave them a big order list. A couple of days later, a semi truck showed up at my house. I think my neighbors were like, what is he doing? Like, why is there all this equipment showing up? But I actually spent several weeks building a lot of the props that you see in the movie. They're basically miniaturized versions of the same equipment racks that we use in the real world. Now, these don't actually collect data. They're meant to go in a movie, not actually be in a research project. So they look right, but they are, hollow on the inside, and they don't have all the electronics. But basically, to scale, they're the exact same thing, just smaller. So I was able to put all this stuff together at home and then take it up into the city and actually interact with the props team and the set design team and the vehicle outfit team and that sort of thing. And what we were able to do was take the real science vehicles that we use every day here at the National Severe Storms Laboratory, that we take out into the field and we pelt with hail and we take observations around tornadoes, and then turn that into what you see in the movie. And I was so excited to be a part of this. I actually got to go up to the warehouse where they were getting all the vehicles ready, so you can see some of the vehicles from the movie, like Tyler's truck and the Storm Par vehicles. Jeb's SUV is back there in the back. Lily's van is in there. And I actually installed the equipment racks that we have on the vehicles to make sure that they weren't going to move and that it made sense. I spent a lot of time working with the different teams to kind of advise them on, like, hey, put this weather station here. Make sure you have this many antennas on that car. This car needs more cameras to look more authentic, that sort of thing, to make the cars believable as they were part of this storm chasing group in this storm chasing universe. And even on the inside of what eventually became the Lion van that's part of the Storm Par team, all these equipment racks with screens and monitors, being able to see all of that built out and what it eventually came to look like in the final film was just a truly incredible experience. I mean, these guys are amazing at what they do and what they can create in a phenomenally short period of time. So it was a lot of fun to not only build the equipment, but then to take it on set and actually get it installed on those vehicles. Now, another part that I had a big hand in was the graphics, right? We got to make sure that the graphics look right. And there's a team, there's teams all over the place, right? If you see a movie and there's 20 people in the movie on screen, there's 400 people behind the scenes that are actually working incredibly hard and long hours and years even to make these movies happen, right? And the team that is responsible for graphics, so anything that shows up on like a TV screen, a monitor, a cell phone, a laptop, anything like that, it's called the playback group. And it's their job to design those graphics to make sure that they look right. And I mean, as an example, if anybody's seen Iron Man, this is the same guys, that built the Jarvis interface from the original Iron Man. I mean, just absolutely iconic imagery that sticks in your head that you just see in a movie and you're like, oh, that makes total sense. And it sets the mood in the scene. Well, somebody had to actually create that graphic because a lot of this stuff doesn't exist anywhere else, right? So these guys are amazingly good at what they do, but they need input for things. And the biggest challenge that they face is that they want to make sure that it's right, that it's beyond reproach, that nobody's going to be able to nitpick it, because we all do that, right? If there's any Game of Thrones fans in here, there are multiple scenes in Game of Thrones where an actor or an actress had maybe a Starbucks cup or something, and they set it down on a desk, and then that didn't get removed from the show. So if you watch closely, you can see some of those elements in the backgrounds of things. There's a pretty famous scene in the original Avengers movie where there's a dent on a car that from one scene to the next, like within a few frames, the dent just magically fixes itself. So some inconsistencies there. And these little details may not seem like they're that big, but they matter tremendously to the fan base and to people that really enjoy the movie. And as a really good counterpoint to that, or an example of that, if you think back to the original Twister movie, there's a scene in the movie where they launch Dorothy into the tornado and they show a radar image. And that radar image, if you didn't know, is completely wrong. It's entirely not representative of anything realistic. It's clear air data. They grabbed a velocity image from a radar very last minute. There's not even a storm on that radar, and they used it to represent this incredibly chaotic, tornadic signature. And it's completely wrong. And every meteorologist, like, that's one of the things that we learn almost immediately when you're learning through all those classes and getting used to looking at radar data. And then you go back and you watch the movie and you're like, wait, that detail's not right. And then it bugs you, and then you can't sleep at night, or maybe that's just me. Right. So what we decided to do with this movie, my personal goal, was to make sure that none of that happened. So I actually worked very closely with the playback group to hand select real radar data cases for all of the radar imagery that you see in the movie. None of this is fake. These are all very real cases. Now, they may not be physically in the right location, right? That left image there, that's from one of the scenes kind of early on in the movie where they're talking about things. That radar imagery is actually from Southwest Kansas. We just sort of moved it down into the Texas and Oklahoma region to fit the narrative of the story. But the radar echoes that you see, all the warnings that you see, those are real warnings. Those are real radar data, real echoes. So that way we could actually represent, a real environment. And to that point, I circled one of those there. There was a Twitter post that went around where somebody was nitpicking that radar box, or that warning box, and saying, hey, like, oh, they messed this up. They didn't draw this in the right place. This one doesn't make sense. And in that particular case, that warning is very real. There was a very real tornado warning relative to the storms. It was issued in that location. So it is actually accurate. Just it didn't match up with the storm. There was an issue with the warning coordinates, I think. So it's very real data, and it actually created a really fun discussion on Twitter about it. So then we, do this with all of the other radar imagery that you see, trying to pick real radar data cases that match what the events in the story are unfolding as, so that anybody that takes a screenshot of this and looks at it can't nitpick it apart and be like, oh, that doesn't match the intensity of this storm, that sort of thing. So this was a really fun challenge for me, was to try to give them the radar imagery that worked for this. And that included also helping them design and craft a lot of the other graphics that you see in the movie, like the tornado simulations and, launching Dorothy into the storm and that sort of thing. And what happens when the different storm PAR units come online and what it's supposed to look like. There's a lot of different imagery that only shows for like maybe a half second on the movie, but it's really critically important to how the movie progresses. So we have to get it right. And all of this is based on real knowledge that we have, or real data that we have, of how storm structure works and looks, and how everything feeds together to create these boundaries, for example, at the surface that form tornadoes, which we're going to talk about here in a little bit. So there was a lot of, prep work leading up to the movie, and then we actually got to shoot the movie, which was a ton of fun. I'm going to throw a couple of pictures up here, just sort of some background scenes of filming and some of the different things that they were using to try to make the shots that they wanted. I got to spend a lot of time on set working with the director and with the actors, helping, dialogue and lines and things like that to make sure that there were, as accurate representations of the real world as we could do. And then seeing how they use different lighting techniques and sound stages and that sort of thing to create the special effect look that you see in the final product was fascinating to me, because I guess I didn't realize how many different times you have to shoot a single scene just to get all of those different camera angles and looks to make it feel very real and engaging and authentic. And I think that hard work shows in how the movie looked on the big screen, which was a ton of fun. And then the final thing that I'm going to point out here was there's a number of scenes that take place in a barn that's sort of Kate's home. She's where she did a lot of her work as a student, and later on. There's a lot of neat little Easter eggs that are actually hidden in that scene, some of which include actual notebooks of mine and a few other graduate students here at OU that are very real, that are from the studies that we all take. Some of the notebooks that are laying there are from my dissertation work. So it was a lot of fun to see that kind of stuff, make its way into the movie to sort of give that authenticity to it. And then obviously we did get to go to the premieres, which was a ton of fun, both in LA and in Oklahoma City. Got to take a couple of good photos with everybody and have a really enjoyable time seeing the movie for the first time. That also included rebuilding some of the vehicles very last minute for the red carpet event in LA. Actually pulled the props back out of storage and got them back on the vehicles, which was a lot of work, but it was a ton of fun. And I really got to enjoy the sort of culmination with that, with what is now a good group of friends from the making of the movie that I'm going to cherish forever. So there was a ton of effort in making this movie as authentic and real as possible, right? And we've talked a little bit about that. But how does that mimic the real science that's going on here at the National Sphere Storms Laboratory? Where do we step out of Hollywood and step into the real science that's going on? And that's what we're going to talk about now. So a lot of people are familiar with tornadoes, but not everybody experiences them as often as we do here in maybe Oklahoma. If I ask people if they've seen a tornado here, even like 6-year-old kids are like, yeah, I've seen like 3. It's just basically common knowledge that you're going to see one here, but not everybody's as familiar with tornadoes as we are here. So if you aren't as familiar, tornadoes are some of the most violent weather phenomena on the planet. They can be incredibly destructive. They can also be very beautiful, but that's a very delicate balance of emotions there when we're talking about these things, because we do realize how destructive and violent that they can be. Winds often exceed 200 miles an hour in these things. And there are some tornadoes that are over 300 mile an hour winds. So in a very small space, you can have incredibly high wind speeds that can cause just utter destruction for anything they hit. On average, they're about 100 yards wide or so, but that diameter can vary greatly. And there's some very large tornadoes that are out there. And they come in many forms and many names. They all come from a rotating, what's called a mesocyclone. It's that updraft that's sort of rotating and spinning as it goes up. But tornadoes, twisters, vortexes, they're all the same thing, right? The only real difference are land spouts, which aren't really associated with a mesocyclone. They can form on clear days when there's not even a storm, but they start at the surface and they work their way upward. And that's sort of the main difference between land spouts and, tornadoes. Water spouts are just tornadoes. They're just over the water. I don't know why we decided to have a different name with it, but we have. As soon as a water spout moves on land, it's now called a tornado, and there's a lot of arguments about that. So it's a fun little niche thing, but they're essentially the same thing, and they're very, very destructive. So when and where do tornadoes form? And this question has actually come up a lot following the movie, because people are really curious, like, hey, we saw like 7 different tornadoes in this movie. Like, where do they happen, right? And it turns out that they occur all over the world, anytime, day or night, time of year, doesn't matter. If the conditions are right, you can get tornadoes. I haven't checked Antarctica or Greenland or Iceland or anything like that to see if they have tornadoes. I don't know if the penguins down in Antarctica have seen some things that maybe we need to ask them about, but tornadoes happen all over the world if the conditions are right. And in the United States, all 50 states at some point in our history has seen a tornado. Now, the Intermountain West region gets a little less dense, right? And then when you get out there on some of the mountain ranges in the east, like the Appalachians, it's not as common as it is in sort of the central plains and the southeast part of the United States. But we do see those tornado tracks absolutely everywhere. And if you look at a density of those, and this conversation has really taken off in the last couple of months, is this sort of concept of Tornado Alley, and is it changing, right? Tornado Alley has traditionally been the central part of the United States, Oklahoma, Kansas, Texas, Nebraska, that sort of region. And then there's this secondary area that a lot of people refer to as Dixie Alley that is in sort of the Louisiana, Mississippi, Georgia, that kind of region, right? And peak tornado season for the Central Plains is like mid-April through mid-June. That's where a lot of our severe weather happens, although we did have a supercell in Oklahoma City last night with a lot of hail, which was a lot of fun. But it's typically tied to the diurnal cycle, which means they happen late afternoon and they kind of die off after night. The Southeast, on the other hand, experiences tornadoes a lot more frequently. It's also generally shifted towards the winter months. That's when their season is most active, and they can occur at any time of day or night, which raises a lot of really unique and interesting challenges when you're communicating that information, because the vulnerability in the Southeast is significantly higher. There's a lot more rural counties and rural communities. There's a lot more trees. They're harder to see. They happen at night. They move faster. There's a lot of challenges with just communicating that warning information on those tornado events when they do happen down there. And that's something that we're going to talk about. So how do they actually form, right? In the most basic sense, a tornado is a downward extension of rotation from a larger parent circulation known as a mesocyclone. And there's a lot of words in that, but basically you got a big supercell thunderstorm. You've got warm, moist air at the surface that's fueling the storm because you've got cold, dry air aloft. So when that air rises, it's now positively buoyant like a fire. You know, that hot air just continues to rise until it finds air that's warmer than it. So it goes up and we create this big, massive thunderstorm. And the changes with wind speed and wind direction as you go up through the atmosphere actually cause that storm to rotate. Now, all that air going up, it's got to come back down somewhere. So we actually have two areas in the storm. There's an area called the forward flank downdraft and the rear flank downdraft. And this air, as it's coming down sort of around that main core of the storm, is colder, it's denser, it's got more precip in it than the environmental air that's sort of fueling things. And as you have these competing air masses, those boundaries actually create what we think are the origins of the rotation for tornadoes. And that's something that we're actually studying today in our real, science research that we're doing that doesn't involve launching Dorothy into things. We're actually studying a lot of these thermodynamic things or the temperature differences between those environments and how that feeds into creating a tornadic circulation. So I'm going to throw a couple of things up here. There's probably a few people watching this that are panicking at this point because like, oh my God, we're going to start deriving equations and math and all this. I didn't sign up for this at lunch. And the point of all of this is basically to say that these boundaries that we're seeing by doing some really, really high resolution model simulations are really what's driving a lot of these tornadic storms. And those boundaries, the reason that air is rotating is because if you have cold air and warm air next to each other, the Earth tries to balance it out, right? And it causes this balancing act by creating some rotation. Imagine you took a football and you threw it in a perfect spiral, which I definitely can't do. But if you threw a perfect spiral, if you replace that spiraling football with a horizontal column of air, that's the same way that the storm is creating this rotating air at the surface. And then how that gets fed into the tornadic vortex is what's driving it. And that's what we're trying to study today. Can we actually see these boundaries in the real world? Can we observe them in our observations outside, essentially? And, how can we predict this type of stuff, right? Everybody wants to know, can we predict tornadoes? Our understanding of large-scale environments that are supportive of tornadoes has increased dramatically over the last several decades, largely part to the field projects that we've done to study things. In the 1980s, your average warning time was like 4 or 5 minutes, which is not a whole lot of time to take action. Now it's closer to 20 minutes. And we've actually got some studies that we're starting to look at about what happens if we give people more warning. Like, do we still get the same level of response and action? And the short answer is no. People actually feel like if they have more time, they stop paying attention. So there's some interesting social behaviors that are going on there. But we generally know days that are likely to produce tornadoes, especially big outbreak days. Those are usually pretty obvious. The challenge is that we don't understand why one storm will produce a tornado and one won't. And that's the type of questions that we're having to ask and answer now, right? Like that storm's got a tornado that's been on the ground for 2 hours and is 2 miles wide, but the storm 20 miles to its south can't produce any meaningful circulations, right? And they're in the same environment. So what's different? What gives? The large-scale outlooks, if you didn't know, are issued by NOAA's Storm Prediction Center, which is here in the National Weather Center in Norman, and they do those outlooks for the entire country. But the individual, like tornado warnings, thunderstorm warnings, that sort of thing, those come from your local weather service office. And there's a lot of close ties to emergency managers and officials, news media to sort of communicate that information. And there's a very good reason for that. That's so they understand like the local conditions a little bit better. They're a little more tied to the community. There's a lot of advantages to having the weather service segmented out like that. It makes it more responsive to those local environments. So what don't we know, right? I said earlier, like we can't predict why one storm produces a tornado and one doesn't. Our observations are great, but the truth is we're still missing part of the tornado because we're not sampling the base. We're not sampling that area right next to the ground where it sort of connects down. And that's where all of these sort of pieces of this like puzzle essentially is coming together to create that rotation, right? We just don't fully understand how or why tornadoes form or what dictates their behavior. And there's a lot of simulations that we've done recently with big computer models that have shown that this air that's feeding into the tornado sort of erupts vertically right as you get close to the vortex. And the strongest winds near the ground are mixing to lower speeds aloft. So we're really, really focusing in on that area right near the surface that's causing all of that destruction. That's what we see and we feel, right? It's extremely difficult to get safely close to these things and collect observations. There are a few vehicles, spoiler alert, there are a few vehicles that people have made that have spikes on them that will sort of hold them in some lower end tornadoes. They're really good for standing up to the wind. I don't know how well they would stand up to large debris if they got hit with that. But there are a few people that do that. But it is really, really dangerous. It's not like, please, nobody go out and do this. It is incredibly dangerous to be close to these things. Please leave that to the professionals. But, there are some other questions here. Point observations versus volume observations. Is it worth it to take a single point observation in something this complex? Or do we actually need something like a radar or a LiDAR to get volume observations? Should it be mobile or fixed? Do we need to follow the storm, or can we just wait for it to come to us? That sort of thing. And I can tell you the answer on that one is that it needs to be mobile. If we build a fixed stationary site, we might wait 20 or 30 years before a storm goes right through that area. So there's a lot of unique challenges that are associated with doing this. And that's how we study these events, is we use a lot of different technology, mobile radars, UAS, mobile mesonet trucks, weather balloons, surface observing stations that we drop out to sort of create these different observations in different puzzles that we can put together to create that large picture, right? Like if you're going to try to tell me what the picture looks like on a puzzle, you don't do it with just the edge pieces. You got to have a bunch of different pieces in the middle. So that's why we use so many different types of tools and equipment and strategies to try to observe these things. And if we go back and we roll back the clock and all the way to the early 2010s, the Vortex 2 project was going on at the time, which arguably is the best and most aptly named field project ever. Stands for the verification of the origins of rotation in tornadoes experiment. It just sounds so cool, right? And it was to study tornadoes. There was an original Vortex project back in the mid-90s. Over 100 scientists were in the field for this project. Various state and federal, public, private, even international partners all over the Central Plains studying tornadoes, some of the most well-studied cases in tornado research history. There's a picture of the Goshen County tornado, which was pretty famous out of this project up in Goshen County, Wyoming. If you look closely, maybe you have the resolution, you can see some very large hailstones that are going to come back up here in a picture or two that were falling. We were actually on the north side of that tornado looking at it, collecting some of our observations in that area. It was fully mobile. We drove 10,000 plus miles a year just between the months of May and June. And that was really like mid-May to mid-June. So it was a lot of driving, different hotel every night. It was a huge logistical nightmare trying to figure out hotel rooms for 100 plus different scientists in the field. We had probably 50 different vehicles, right? Multi-million-dollar project. And the part of that is because with so many different organizations and institutions, it's a lot of money just to get all those people out into the field and to pay for the equipment and the travel and that sort of thing. But we even had to budget for windshields in the vehicles because you can see the minivans that we were driving at the time did not have a hail cage. So we actually had a budget of like 4 or 5 windshields per vehicle. I'm actually fairly convinced that my Mountain Dew bottles at that point were holding up the windshield's integrity because it was so cratered with hail. So this is part of what led to the creation of the hail cages that we have now on our vehicles. But a lot of moving parts with these types of projects, massive, massive project. And it gave us a lot of understanding about those large scale conditions. And that's what led to a lot of the work in finding some of these higher fidelity boundaries that we see in our really high end research models that we're running now. But it was a huge logistical challenge. So now that we know that these boundaries exist from some of our previous work, are there ways that we can sort of focus in on those and try to study those? And Taurus, which is a really good example of that. We did it 3 years. You'll notice a gap there in the middle where COVID happened. We basically just didn't go outside for about 2 years. So there's a lot of difficulties with that. But, can we go out and we observe these boundaries and how it's relating to a tornado out in the real world on a real storm? And we did that by using a ton of different types of equipment. At this point, we're actually starting to bring UAVs into the fold where we're taking vertical observations with drones in areas that we can't get, much like Lily was doing in the movie, right? Like Lily had her drone up. She was taking video observations, and she even had some temperature and humidity stuff there towards the end that they added to get those numbers. We're doing the same thing in the real world with UAVs. We've even had full aircraft that are instrumented near the storm that are taking those observations. So a lot of the imagery and sort of the ideas that you see in that movie, those are things that we're doing today, right? Using drones to collect observations in areas off the road and above the surface that we just can't put human equipment, right? That's driven by or flown by a human. You can put a UAV in places you should not put an aircraft. I'll say that. But we basically operated in the Central Plains region, anywhere that we had permission to sort of fly that drone. That's sort of the area that's marked out there. Drove a lot over the 3 different years that we ran this. And it was a joint operation between University of Nebraska at Lincoln, the University of Colorado in Boulder, Texas Tech, University of Oklahoma, and the National Severe Storms Laboratory. So a lot of different partners all working together to try to answer those questions. And we answered some, but we asked a few more, which is how any good research project does. But what about the Southeast? I mentioned Dixie Alley earlier. We actually did a project not too long ago, just last couple of years, looking at storms in the Southeast. Taurus and Vortex, these were focused on Central Plains stuff. Perils specifically wanted to look at storms in the Southeast. And this is really difficult to do because there's a lot of trees and the road network doesn't make sense. They're not straight roads. They deviate off into place. A lot of our equipment needs line of sight to the object to be able to sample it. So how does that work in a forest? So we actually created a planning team that went out and did site selections in very specific regions well ahead of time. And rather than just sort of picking a deployment site on the fly, we would actually pick those sites days in advance when we knew there was going to be an event and then go set up things. So there's a lot of challenges in how we do this type of research, right? And it varies depending on where we are. A couple of different types of equipment that we started to use. We had mobile radar trucks that were faster, they were more nimble, had to get closer to see things, but they give us information at a higher resolution, very similar to how the StormPAR works, right? That's where some of that inspiration came from. We use mobile, sticknet type things from Texas Tech that are meant to be stationary and just take observations as the storm moves over. We had lightning mapping arrays to sort of map the electrical activity in storms, and launching rapid succession small balloons called windsondes that give us vertical profiles of observations in the near vicinity of supercells so that we can understand what changes are going on with things. And it was pretty successful. We saw a lot of different tornadoes in the region, including the Rolling Fork tornado, if anybody remembers that one, which was an EF4 that hit Rolling Fork and unfortunately caused a lot of destruction and damage in that area. But we sampled a number of different storms, still looking at a lot of this data. I mean, there's a lot to unpack with this stuff. It was a huge project with a lot of different partners in it, way too many to list. There's a lot of new research that's coming out with this, so we're still looking at it. But recently, we've been doing a project called LIFT, which is really focusing in on the near surface conditions of tornadoes, really trying to understand that ground connection and that lowest, 50 or even 100 meters of those tornadoes. So it's smaller, it's a little more nimble, right? Less teams, vehicles that are highly mobile, trying to get in close so that we can get those observations. And what's different is that we're not really starting and stopping this project. It's sort of just whenever there's an event, we go out and we do it, right? Focusing closer to home, that keeps travel down a little bit, makes it easier to take students out in the field to teach that next generation, which is something that we really, really focus on here at OU and NSSL. But the idea with this is to position our vehicles in front of that tornado and let that tornado sort of pass between us in my very professional animation that I've created there. And we're sort of combining different equipment, right? We've got a couple of our mobile radars that are supposed to be positioned very purposefully to where they can capture radar observations sort of in an overlapping pattern over that tornado, which is exactly what the StormPAR team was doing with their StormPAR units in the movie, right? With those multiple radar images from different angles and different positions, we can create a three-dimensional wind retrieval of what that vortex looks like. And that's the whole goal, is to try to get those observations. We're in the process of developing some deployable vertically pointing radars that aren't quite ready yet, but we're getting ready to put those out into the field. So there's a lot of new technology and new advancements in science that we're utilizing in studies like this to really try to answer some of these hard to reach questions. And some of the data looks absolutely incredible. Some of this was shared on Twitter from a couple of people, but this is radar imagery that's not actually of the whole storm. It's really just of the tornado. And you can actually see some of the spiral bands inside some of these circulations, which is just truly remarkable data that the radar was able to collect. So we're all really excited to try to dig into some of this stuff that we just collected, in May this year, earlier on. And we can actually combine data from different instruments as well, right? We've got radar imagery there. We've got LiDAR data that's overlaid on top of it. So we can get a finer resolution of what those low-level winds look like in those really hard to reach places that we haven't really been able to sample well in the past. So this is a really unique challenge that we're sort of facing now, is how do we get these instruments in there, get close, get the observations, and then safely get back out without putting anybody in danger or any of our equipment in danger. And these are some of the challenges that we're facing with these projects, right? And we've talked a lot about tornadoes, but one of the other things that I did want to kind of throw out there, because it's a really exciting new development. Supercells not only produce tornadoes, but they also produce a lot of hail. And I don't know if you guys get a whole lot of hail out in North Carolina, but we do get hail here. We had some yesterday. And hail observations for decades has been post-impact, where it falls, and then once it's done, you go outside, you pick it up, you find the biggest stone you can, you take a measurement of it, you take a selfie with it, you post it on Twitter, you tag the Weather Service, and that's your observation. And that's a problem, because that stone is melted, it's broken. It's an oversimplification. It's not measuring all the stones that are out in your yard. It's just measuring that one. And we really need observations of those hailstones in real time, like what actually fell, to connect that back to the radar imagery that we're seeing to make our warning process better, which is the ultimate goal. So we really need a way to observe hail in complete free fall. So at the National Severe Storms Laboratory, I've created a new sort of equipment or deployable, instrument, whatever you want to call it. It's essentially a hail camera on the back of a vehicle, so that we can drive in front of the hail, find where it's going to fall, park, and then just let the vehicle get absolutely pummeled with the largest stones that I can find. And the way this works is there are some insanely fast cameras that shoot 4K footage at 330 frames a second out of each camera, which is just wildly fast. And with those two cameras, we can actually triangulate where the stone is, so we can figure out its size, shape, velocity, rotation rate. We can see water on the stone melting and it dripping off in the air as it falls through the environment, which is truly incredible. But to do that, I need a ton of light. So the LEDs that you see produce a total of 256,000 lumens of light, which is brighter than the sun. The sun only puts out about 170,000 lumens per square meter at the surface. So the back of this truck is legitimately brighter than the sun. If you're standing anywhere within a quarter mile of it, you need eclipse glasses to look at it. It is wildly bright. So I have to be really careful where I deploy this thing. But the imagery that we've started to collect with this has been truly breathtaking to see. But it is capable of observing hail in total free fall, which is just going to be an absolute game changer for how we do observations going forward. And this is a really unique advantage of the Severe Storms Lab here, which is to create new experimental platforms like this and really push that observational capacity forward and do exciting new research like this and take it out into the field and collect those observations. So with that, I know we've covered a lot of things. We talked about twisters and we talked about storm research and how the sort of two overlap. So I'm going to actually pause and stop there and ask and see if you guys have any questions at all. If there's anything you're curious about, absolutely happy to answer them.
All right. Amazing stuff. Incredible. I'm in awe. One of the experiences that you've gotten to have, but also of the work that you're doing and the devices that you've built. We were chatting down here during the talk. We're glad you work for the Weather Service and not like the Department of Defense, I think.
It is a ton of fun to actually create some of the equipment that we use. And I think what I enjoy so much about my job is there's no set path, right? Like we don't have blueprints that we're following. There's a lot of creativity associated with it that we get to kind of make these things up out of scratch. And the team that I work with, the guys that I kind of share this office space with, we're just truly a really fun group that just loves creating new equipment.
Very cool. So one of the first questions that came in online for you, in terms of our instruments and technology, in what ways are we observing storms better than we did during Vortex 2?
Right, so that's a great question. A lot of our equipment that we use on the mesonettes, for example, that hasn't really changed, right? It's basic stuff. It's wind speed and wind direction. but it's where we're putting the vehicles and the addition of the hail net that we have on top that allows us to get in regions that we haven't been able to safely get before. Some of the bigger changes that we're really seeing outside of that are in our radar data. Our radars have gotten a lot better. We're creating new systems all the time that are faster, that are more rapidly scanning. And when you start talking about PAR technology, that's where really the game starts to change, because we can sample the entire atmosphere in seconds versus minutes that it took to try to sample things before. So we can see a higher resolution of things and see it changing in different ways. We're starting to look at microphysics observations, which means we're looking at distributions of raindrops and snowflakes and things in different parts of the storm, and how that's actually creating the environmental boundaries that we see at the surface. So while Vortex 2 was an incredible project and it was a lot of fun and we learned a lot with it, we're moving forward with those observations and adding things like phased array radar and vertical observations of raindrops and that sort of thing to really dig into the harder to reach questions.
Similarly, Glenn is asking, is computer modeling playing any role in tornado research, or is there not enough data available yet? And you showed us a few models.
Absolutely. Yeah.
Like
Absolutely,
some of
it's playing a role.
Models and stuff like that.
Right.
Yeah. Okay.
Right. So what's really interesting about things, our computer models have naturally increased in their capability as we've moved forward with technology. So our forecast models get higher resolution and things like that. But when you start talking about like the supercomputing stuff, which we didn't have access to 15 or 20 years ago, those models are able to simulate things on a scale that we've never been able to look at before. So a lot of those high resolution simulations, and I showed a couple of them about midway through the talk, actually observed boundaries and interactions with things that we didn't think existed before, or we'd only theorized. And then we see a computer that spits it out and says, hey, this is really important to this tornado in this model that I've created. So what we've seen is sort of this shift where we actually started doing research projects following what models have shown or seen, trying to decide, okay, is this model latching onto something that's physical, that's real, that we can mimic or see in the real world, or is it just completely creating something that's false and not actually a real thing? So a lot of the research that we're doing now actually has been driven by some of those supercomputing models and some of those higher resolution simulations. So it is a very good feedback process, and we can take the data that we collect and then push it back into the model to see what new changes the model makes and does it get more accurate and things like that. And those are some really exciting projects that we're also working on here at the lab, where we're actually ingesting additional observations with machine learning and AI and things like that to try to take those observations in and then create a better forecast going forward from that point that we wouldn't have had we not taken those observations.
Excellent. Joe wants to know, is the way that Kate was trying to stop a tornado at the end of the movie a reality? Come on, give it to us straight.
Yeah, I'll give it to you straight. So that's a fantastic question. So there's a two-part answer to this, and I'll start off with the answer to your question first, and then a supplemental answer. So the theory behind it is technically correct, right? The idea that a tornado could be disrupted is sort of a real idea, right? It's based on a very delicate balance of conditions that are required to produce that rotation. So if you were able to disrupt it in a way that sort of changed those conditions at the surface, you could, in theory, alter the either direction of the tornado or the intensity of the tornado, or dissipate the tornado entirely. Now, the way in which they're doing it isn't quite perfect, right? They're launching this polymer which would absorb a lot of the moisture. And I think what actually would end up happening, rather than creating a really strong cold pool that pushed to the surface and undercut the tornado, which is absolutely a real process. I see storms themselves do that all the time, where they produce too much rain. That rain gets down to the surface and it shoots out this really strong blast of cold air, like a wedge that just cuts the tornado off. That was the premise of the movie. But the reality is, if you were actually able to do that in the real world, you probably end up creating a heat burst instead. Because when you remove all of that water and then you force that air down, it's going to compressionally heat as it goes down. So it would actually probably go the other way, right? So in theory, Yes, technically you could probably do that. And I'm putting a lot of stressor points on that one, right? Here's the part they don't talk about. You would probably create a bigger environmental hazard trying to do that than you would if you just let the tornado happen in the first place, right? Because you're going to dump all kinds of chemicals all over the ground. Every farmer in 100 miles is going to be pissed off at you because there's going to be like diaper polymer all over their fields. It'd just be a toxic wasteland essentially. The scale at which you would need it is also something that is vastly underdone in the movie. They take a trailer and then they dump some chemicals in it and it dissipates this tornado. The amount of energy that is contained in a supercell or in a tornado is unfathomably large. So you would need like literal tons, like a C-130 full of this stuff to even have a small dent of a chance at making any difference in things. It's just a huge scaling problem. But deeper than that, there's a larger question here, which is, should we, even if we could disrupt a tornado, is it a good idea? The atmosphere is balancing energy, right? Every tornado, every lightning, every hailstone, every hurricane, every thunderstorm is the Earth attempting to get rid of energy imbalances in different parts of the planet. It's too hot at the equator. It's too cold at the poles. It wants a neutral, mid 70s temperature everywhere, right? So that's the weather that we experience. What happens if you throw a wrench into that engine, right? That energy needs to be dissipated, and it will dissipate itself somewhere, somehow. So if we start playing with the atmosphere like that and we start blocking that energy release, we risk creating a much bigger problem down the road, right? It's way, 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 way better to just let the situation happen, let the tornado happen, but instead focus on building tornado resilient structures and infrastructure so that we're not, at risk from a humanity perspective while letting Mother Nature do her thing. So that's my 2 cents on it.
Dr. Waugh, I think you just wrote the plot for Twister Zurzers.
Yeah. If anybody's listening from Universal Studios, I've got so many ideas for the next movie. Hit me up, ready to go.
We do a decade's worth of stopping all of the tornadoes, and then the result is we messed with nature, and nature comes for vengeance.
Right. Like Twisters 3, like Mother Nature fights back or something like that.
See, exactly. See, it's already written itself. It's already written itself. So let me get to some more of these good questions for you. This is a great question. Who services and maintains all of that equipment you showed us?
That's an excellent question. Most of that equipment, at least on the National Severe Storms Laboratory side, comes out of the division that I work in. And there are 3 whole people that work in this division and then a graduate student right now. So there's like 4 of us that work down here that really build and maintain a lot of this equipment. And it is a full-time job. When we go out into the field and we collect these observations, for example, I promise you things break. And it's always something that like you wouldn't think would happen, right? It's something weird or stupid that you like, surely that's not going to be the failure point. So when we go out in the field, I actually take a ton of spare equipment with me so that we can repair anything, anywhere, no matter what happens. I've got tools, I've got parts, I've got materials, and if I don't have it, I can go buy it, because we have to be able to fix things when they break out in the field. And then when it comes back, there's months of maintenance and things that, improvements that we're making on this kind of stuff. So it is a constant effort to keep all of that equipment going, for sure.
Are there more tornadoes now than in the past?
Great question. Phenomenal question. So that question has also come up a lot recently. One of the things that the movie sort of didn't really address, but it sort of created a space for this conversation, was the idea of climate change. And are we seeing changes in tornado patterns? Is Tornado Alley shifting? That sort of thing. And the reality is if you look at climatology, tornadoes it's not really moving around. At any point, if you picked this 5-year or 10-year period or that 5 or 10-year period, you're going to see hot spots, right? There's ebbs and flows to where tornadoes occur. And it's not really shifting so much as it is expanding. We're seeing tornadoes happen in a wider region over like longer periods of the year at different times of day, that sort of thing. But the average number of tornadoes doesn't really change a whole lot. I think it's about 1,200 a year total across the United States, at least. And we don't really see the average number change from year to year, maybe +1 or 2, a given different year or whatever. but it's the number of days that we see tornadoes. That's what's changing. So if you go back a couple decades, it was about 150 days a year that we would see tornadoes, right? On any given of one of those 150 days, you'd see some number of tornadoes. And what we're seeing is a shift towards fewer total days, but more tornadoes when we do have days. So like a more extreme event, like an outbreak type thing, right? So now it's down to about 100 total days of tornadoes, but the same number of total tornadoes. So that's sort of the shift that we're seeing. And this is all taking into account the fact that like population has changed and everybody has a cell phone now. I guarantee you there's not a tornado that happens in the country that is not on social media within 10 seconds of it happening. So we're getting better at observing them. We're certainly seeing that sort of influence on things. But even if you go back and you just look at conditions of things, that's essentially the shift that we're seeing is same total number, but focused in on fewer days.
Excellent stuff. Very interesting. All right. Now, you mentioned drones and UAVs in your presentation. David is wanting to know about flying them into tornadoes and the kinds of data that they collect. Can you tell me a little bit more about what the drones do, where they go exactly when they're collecting data?
Right. So this has actually been a really unique challenge that we've been working on over the last probably 5 or 10 years. And there's different groups that have really been doing it, where drones have started to increase in their capability and longevity to be able to put themselves in places like this, right? What we're using drones for here at the lab are sort of two things. One is observations that I'm going to say are in the vicinity of tornadoes. So they're not flying into it, but they're sort of flying in front of it, around it, that sort of thing, taking observations in a vertical sense of like temperature, pressure, wind speed, wind direction, relative humidity, the same variables that we're taking at the surface, but now we can get vertical profiles of those as well. And the idea is to sort of capture that in front of the tornado so that we understand what's driving it. And then there's also a second effort that uses drones with cameras to do damage survey work, because you can get a unique perspective from the damage that they cause, if you're in the air, right, in a plane or a drone. Drone's just easier to put up than getting, a whole flight planned or things like that. So we're using drones for a couple of different things. There are a few groups that are starting to play around with flying drones into tornadoes and things like that. But here's where the challenges come in. There are a ton of rules and regulations that we have to follow, or at least should be following, for any other groups that are doing it privately listening, that require us to work with the FAA on what they will allow us to do, right? And 10 years ago, it was super restrictive. We couldn't fly over highways, for example. We had to land and carry it over and then take off again. And we've relaxed some of those, but a lot of the flight regs now require that we maintain visual line of sight on the drones, because they don't want it getting sucked off somewhere and then ending up in open airspace, hitting a plane and causing a horrible accident kind of thing. Now, granted, I don't think there's very many commercial airliners that are flying around tornadoes, but if it got sucked into the updraft, for example, that drone may go somewhere you didn't want it to, right? So there's a lot of rules that we have to sort of toe the line on, and we're working on expanding those to allow observations to get a little bit closer. The biggest challenge that we face is that the winds around these things are incredibly strong. And getting a drone that can survive and hold up in those winds and maintain any sort of control or position is actually quite challenging. Getting a drone that can, hold its position in 100-mile-an-hour wind is a really difficult engineering challenge, and, not just fly for like 3 minutes and then have to come back down. So there's some hardware challenges that we're facing right now that a lot of, really advancing groups and private companies, for example, are working on to try to make those better. I'm really, really excited to see where we take drones in the next 5 or 10 years. I've got some ideas on some things that I think we're going to start trying to do here at the lab that are really going to push that forward.
At any point during the filming of Twisters, when you were on set, did they just come up to you and say, "Do you just want to do this? Should we just get rid of this guy and you could just do it?"
Yeah, so I interacted with the cast a lot. Glenn and I had a lot of conversations about things. Really good group of people, also really deeply interested and committed to their role in understanding the meteorology behind it. I gave them crash courses on storm chasing and what it's like to do tornado research. We had a forecaster by the name of Rick Smith here at the Weather Service office in Norman that provided them like a severe weather 101 course. Isaac, the director, and the production staff was incredibly engaged in trying to learn things. I didn't talk about this, but I did have an opportunity to take Glenn and a few of the others chasing. Glenn, Daisy, and Brandon all went with me. We actually went storm chasing on a day earlier this year. We ended up not seeing a tornado. We got some good storm structure and some lightning and things. But that's probably the truest experience of storm chasing is driving 12 hours and not seeing anything. So they really fell in love with it, and Brandon at least is texting me constantly and being like, "Hey man, like next season I'm out whole time. We're gonna see so many tornadoes." So they were pretty excited about it, and it was a lot of fun to work with them and watch them bring to life something that I'm so passionate about and that I work with here at the Severe Storms Laboratory.
Excellent stuff. Well, Dr. Waugh, thank you so much for being with us on the program today, for sharing, sharing the stories about like the making of the film and your role in it, but also maybe even more importantly, all of the interesting science, important science that's going on that's, improving what we know about these storms, but also how we can respond to them, because ultimately all of that feeds into helping keep people safe, as well as just how cool these things are to study. So thank you.
Absolutely. Anytime, guys.
And thanks everybody for tuning in to today's edition of the Lunchtime Discovery Series. Well, of course, we'll be back here next Wednesday again at noon. We'll be in person in the Daily Planet Theater and online on the museum's YouTube channel. Many thanks to the folks with the Office of Environmental Education and DEQ for helping put this series together, inviting fantastic speakers like Dr. Sean Waugh here. If you want to know who's coming up next, head to eenorthcarolina.org, or the museum's website also has the information, naturalsciences.org. There you can get all the information, including links to join up so that you can be here every single time for these fascinating conversations that we have. Thanks, everybody, for tuning in. Be safe out there, and know that there's cool, smart people looking out for you out there in the world. We'll see you all again real soon. Bye, everybody.